So now that we've talked about all these different Java programming paradigms, let's zero in on the Java Reactive Streams paradigm and talk about its pros and cons. So we're going to talk about its pros and cons within itself and also pros and cons with respect to other Java approaches for programming. So let's go ahead and start first with some of the pros of Java Reactive Streams. So as we've discussed, Java Reactive Streams implement these reactive programming principles, responsiveness, resilience, elasticity, and message-driven. And the goal of doing this is to achieve a number of benefits. So one benefit you get, which was really sort of one of the initial motivations for this paradigm in the first place, was to have improved resource utilization. And the idea was to support concurrency, or parallelism for that matter, with as few number of threads using a whole bunch of different kinds of thread pools that are optimized for different kinds of behaviors. Sometimes they're optimized for I/O behaviors where they'll be blocking. Other times they're optimized for computation-centric behaviors where you're going to have a lot of stuff running in the background, but they don't have to block. And the goal is really to be able to scale up performance while using relatively few resources. Here's a graph from a paper from a few years ago when WebFlux first came out, and they compared the performance of a WebFlux-based server versus a classic Spring WebMVC style server where there was a pool of threads, a fixed size pool of threads, and synchronous programming. As you can see, as the number of concurrent users went up, the WebFlux approach, which was based on reactive programming, scaled better and kept the latency nice and low and fairly consistent, whereas the one that used the thread pools started, the fixed number of threads in the thread pool with Spring WebMVC started to melt down as the number of users went up. So that was really what was driving people's decisions back in the day, was better utilization of underlying computing resources, especially hardware, memory, and things like that. This is particularly useful for I/O-bound operations in Java programs that use traditional threading models. In other words, everything up until recently with very modern Java when you can have virtual threads. So if you've only got, say, 4 cores or 4 threads or whatever, then if you start trying to download a lot more images or files or movies or whatever, then you have cores, you're not going to be able to take advantage of things. You're going to end up creating traditional Java threads, and they're heavyweight and they're expensive to create and take up a lot of resources and so on and so forth. So improved resource utilization was the name of the game back when this paradigm really began to be popular. Something else it does is it provides a nice, rich set of operators to manage asynchronous data flows and back pressure, which prevents subscribers from being overwhelmed in high-load environments. If you ever see the Lucille Ball video of the chocolate factory with I Love Lucy, you'll get a kick out of it, because this is basically the issue. The chocolate's coming by too quickly for the people to put into the cartons. And so they start stuffing it in their mouths and all kinds of other funny things. So this is also about better resource utilization by being able to apply back pressure. And that's something you get with reactive streams. Another nice thing you get with reactive streams is you can hide the concurrent programming mechanisms. You don't have to use synchronization often. You definitely don't have to create threads, pretty much never. And by doing these encapsulations, it alleviates a bunch of accidental and inherent complexities that would otherwise raise their ugly head if you program with traditional Java threading mechanisms and synchronizers and so on and so forth. Something else you can do if you understand the programming model is you can have enhanced error handling, where you can build resilient systems that will gracefully handle failures. They'll gracefully degrade and not come crashing down wholesale when something fails partially, and be able to maintain the overall functionality of the system even under adverse conditions where some things are indeed failing. So that's another nice benefit of doing this model. Yet another motivation, and this is really a key one, is simplified composition and reuse. You can have very complicated data processing pipelines that, once you understand the paradigm, are relatively easy to understand, maintain, compose, reason about, debug, and so on and so forth. And another cool thing that we get with reactive streams, which we don't get quite as nicely with other Java paradigms like combining completable futures with Java streams is it's integrated more consistently and seamlessly. We're integrating concurrency and asynchrony more seamlessly and in a more coherent manner, because it was done intentionally, than these other paradigms where things are more hybrid. So in effect, concurrent and asynchronous programming starts to look quite a bit like traditional synchronous programming, except things are taking place in the background. Now, very important to note that a lot of these benefits are not unique to reactive streams. So for example, improved resource utilization is something you get also with parallel streams or completable futures. Hiding concurrent programming, parallel streams, completable futures gives you that. Simplifying composition and reuse, you get that. In the case of parallel streams, in the case of completable futures, you can also get enhanced error handling. You may not get seamless integration of paradigms, but it's not as though there's only one way to go. And so that's what segues us into the cons or limitations with Java Reactive Streams platforms. So it's probably fair to say that reactive programming is not appropriate in all situations. It's not a one-size-fits-all magic solution, magic silver bullet that makes all the problems of programming disappear. One of the challenges is complexity. And I think it's probably fair to say, even after a number of years of reactive programming being one of the available paradigms, Java developers in general are more familiar with an object-oriented style of programming than with a reactive style of programming. So there's just a lot more people who have experience. So if you're trying to hire someone for your project, you're more likely to find someone who knows classic object-oriented programming in Java rather than reactive programming. One of the other consequences, and maybe the reason why there's more object-oriented programmers than reactive programmers, is that the reactive style takes longer to learn. That's why we teach a course like this, so you can get experience with it. But in practice, some people have noted that if you have a fairly small project that's not too complicated, you're probably better off sticking with things you know, like object-oriented programming. And it's really only when, system scale and complexity cross some threshold where you're likely to get a better return on investment by using reactive programming instead of more classic styles of programming. And if you watch the video at the link down below, you'll learn more about that. There's also challenges with debugging. Anytime you've got asynchronous or concurrent operations, you get tangled up in a web of complexity that just makes your life more complicated. That's not really a big surprise. And there's also often a lack of meaningful stack traces because you typically have asynchronous callbacks. And when you set a breakpoint and do a backtrace, there's an awful lot of code that you're unfamiliar with and has very little to do with the point where the operation was actually invoked. So this is also a challenge. Now, of course, if you don't write bugs in the first place, there's no need to debug your code, but that's easier said than done in most cases. It's therefore essential to master the reactive programming learning curve if you want to use it effectively. And of course, that's again one of the themes in this class. We want people to get comfortable using this way of programming because it does come in handy in some cases. And it's probably also worth pointing out that debugging with asynchronous operations and concurrency is a problem in other paradigms. It's not just reactive programming that wrestles with that. Functional programming has similar issues. There are a bunch of different perspectives on reactive programming versus structured concurrency. Take a look at this video. You can see Brian Getz, who's a famous Java architect, who is someone that's written books and articles on Java and given lots of great videos. And his point of view is that this new virtual thread structured concurrency approach, which he's calling Project Loom here, is going to kill reactive programming. That may be a little overstated, but I think it's worth taking a look at his perspective and seeing what you think. On the flip side, there's also another article here, fairly recent, about why we need reactive programming. And it does a good job of explaining how and why and when to apply reactive programming and what the benefits are of reactive programming, which are much in line with what we have talked about earlier in this video as well. So that's the end of our discussion of evaluating the Java programming paradigms.